Hi, I'm Tamar Ziegler. It's a great pleasure and honor for me to introduce the first plenary speaker, Professor David Kazhdan from the Hebrew University. David was born in Moscow in 1946, and he did his PhD under Kirillov in 1969. In 1975, he immigrated to the US and took a position at Harvard University. In 2002, he immigrated to Israel, where he's now a professor at the Einstein Institute of Mathematics at the Hebrew University. Kazhdan has made profound contributions to representation theory and has had tremendous influence in many other areas of mathematics. His ideas have influenced work in many areas, including automorphic representations, differential geometry, representations of finite groups, and number theory. One of his most celebrated results is his foundation work with Lustig on the Kazhdan-Lustig conjecture, which guided the development of geometric representation theory. Kazhdan also introduced the well-known Kazhdan property T, which has important applications in many fields, including lattices in algebraic groups, ergodic theory, geometric group theory, operator algebras, and expanders. Kazhdan held a MacArthur Fellowship. He's a member of the US National Academy of Sciences, the Israeli Academy of Sciences and Humanities, and Academia Europaea, and the American Academy of Arts and Sciences. In 2012, he was awarded the Israel Prize, and in 2020, he received the Shaw Prize in Mathematics. Let me finally add on a personal note that Kazhdan's excitement with any new interesting mathematics in any field is really great and inspiring to be around. I hereby invite David Kazhdan to deliver his plenary talk on the Langlands correspondence for curves over local fields.
Okay, in this talk, I present results and conjectures of my work with Braverman, Ettinghoff, Frenkel, and Polishuk on an extension of unramified Langlands correspondence to fields of rational function on curves over local fields. Given a curve in a group, the unramified Langlands correspondence consists of construction, a commutative Hecke algebra acting on a vector space, and a description of its spectrum in terms of a dual group. In this talk, I assume that G is the simplest simple group PGL2 and write H for Hecke algebra. I present three constructions of Hecke algebras. The first in the case of non-archimedian local fields, and the other two in the general case. The conjectural description of the spectrum in terms of a dual group, which is SL2 in this case, exists only for curves over Archimedean fields, and will be discussed in the second approach. Let A be a commutative finally generated algebra, and C a smooth, proper, and geometrically reducible curve of G not G of the spectrum of A, which has non-trivial point. To simplify the presentation, assume that the genus of curve is at least 2. Let ban be the stack which associates with him S of the spectrum of A, the groupoid of G bundles in the fiber product. Since any G bundle in curve comes from a two-dimensional vector bundle, uniquely defined up to twist by line bundle, in the next two definitions, I deal with G bundle as if they were vector bundles. For any R, I denote by R the substack of bundles F not containing line bundles of high degree, and write band stable, which is the same as band 0, for the substack of stable bundles. As well known, band R are open-dense substacks of finite type, and band stable is a spoof scheme. The construction of Hecke algebras uses the Hecke correspondence. The Hecke correspondence of A stack Z of quadruples, where F and G are bundles, V is the point on the curve, I is the embedding of bundle G to F, such that the quotient is a projective A model of rank 1 supported in the point. We have natural projections P and Q, and ZVX is the fibers of Q. It's easy to see that morphism Q is representable with fibers isomorphic to projective lines. Now I start my first approach. In this part of the talk, I assume the ring A is 5. So let A be an Artinian stack of A of locally finite type. I denote by Y the set of isomorphic classes of the object or groupoid of a point, so forth. But meanwhile, the measure of this set, such a measure of a point, is inverse to the number of automorphisms of points, as y is the space of complex valued functions finally supported, H is a corresponding Hilbert space. We have the projection from Z to band and from Z to band times C, P and Q, induce the corresponding operators on the space of function, we pull back and we push forward, where push forward is given from sum over points of the fiber. Here we use the fact that A is a finite ring if the fibers are finite. We define the Hecke morphism as a combination of pull back and push forward, which map from functional band to functional C cross band, and define Hecke operators as a restriction of its morphism to the fibers on the corresponding point. Now, the important thing is operators corresponding to different points of the curve commute and extend to bounded self-adjoint endomorphism in Hilbert space. Let HA be the subalgebra generated by Hecke operators for different points. For any F defined by HA of F, the subspace spanned by application of Hecke algebra to this function F, and we define cuspidal function as a wave function for which we generate finite dimensional subspace. Now, let F be a local non-archimedian field, all the subring of integers, and the maximal ideal. Let C be a smooth curve over O and C any reduction on nth power maximal ideal. So C1 is a curve over a finite field. We have natural notation or NS, NHN of the NHN cusp, the corresponding rings in spaces of function, and define spec n, the spectrum of Hecke and the Hecke algebra acting on this cuspidal function. The cuspidal part of the classical geometric unramified Langlands correspondence proved by Greenfield says the dimension of a cuspidal vector space, when we consider S1, it means curve of a finite field, is Q, essentially Q to the power of 3G minus 3. The spectrum of corresponding Hecke algebra is simple, and so our space is sum of one-dimensional invariant subspace. And the important part is that the subspace is parameterized by conjugated classes of reducible homomorphic fundamental group of the curve to the SL2C. Now I'll be able to, before I formulate the main question of the theorem, says that if you consider curve over square of maximal ideal, the situations in some sense look similar. The dimension of the corresponding space of function is essentially square of the corresponding space for a case of a curve on a finite field. And we obtain action of Hecke algebra by Hermitian operators, so we can consider spectrum of Hecke algebra. And the main question is how to describe whether it's spectrum is interesting, and is it possible to describe it in terms of some local system on C2, which can be considered as a surface of a finite field. I will present some conjectures. From this moment on, the big part of the talk are conjectures with partially proved for curved small genus. The first conjecture, very natural, is that if you consider the corresponding space of function, cuspidal function on a portion by nth power ideal is behave properly. It's finite dimensional space or corresponding dimension. We can ask about spectrum of corresponding Hecke algebra, but I don't have any conjecture. Conjectural spectrum exists only for the curve of Archimedean fields to be discussed later. Now, the plan for the rest of the talk. I present two other constructions of Hecke algebra applicable to cursory arbitrary local fields. One provides a commutative Hecke algebra acting by compact self-adjoint operators on the Hilbert space of half forms on the variety of stable bundle. This construction assumes the convergence of integrals, and this convergence checked only for curves small genus. In the third approach, this action of Hecke algebra is well defined, but the spacing is unfamiliar. This approach leads to interplay between the three constructions. So we start second approach. Let F be a local field. We have a norm map, and if F is non-Archimedean, we have subring of ring of integers. From now on, I assume that C is smooth, completely geometrically reducible chord over F, and as before, that the genus is at least 2. To define the Hilbert space H and the Hecke operators, I use the construction of a space of smooth sections of line bundles over F variety, a variety defined over any local field. So if F is a smooth algebraic variety over a local field F, then the set of F points is endowed with natural topology. I define a space of smooth functions on this set as if field is non-Archimedean, as a function is smooth if it's locally constant. If a field is Archimedean, it's a usual notion of C infinity functions. And I define by S of X the subspace of functions with compact support. For a line bundle, if L is a line bundle and defined by some covering and transition function, we can define the complex line bundle on the set of F points by taking norms of transition function raised in any complex power. Since this line bundle construct a locally trivial with respect to natural topology, one may use the previous definition to delineate the space of smooth sections and subspaces of compactly supported sections. If F is non-Archimedean and variety line bundle are defined over O, then absolute value of transition function is equal to 1, and the corresponding bundle is canonically trivial. Now, the main case we're most interested is the case where our line bundle is canonical bundle on X, and we define S kappa of X as the sections with smooth sections with compact support of kappa's power of the corresponding line bundle. It's easy to see this space S1 of X consists of smooth, compactly supported density or measures of X. So the space S1 half of X, our main player, consists of 1/2 densities, and it is endowed with positive definite Hermitian form. Given two functions F, you multiply, you get the density, you can integrate. When you know by Hx, the Hilbert space completion. As before, we denote by the stack of principal G bundles, and Z, the Hecke correspondence, and consider the corresponding projections, P and Q, as before. The conjectural definition of Hecke operator is based on the following result. If you take half density on one and take a pullback, which of the and restrict this pullback to the fiber of Q, you obtain a density with values in some line, one-dimensional space. Now we can try to define the Hecke operator, as before, as a push forward integrated along the fibers of this measure. But our space, our density is defined on the open subspace of corresponding projective line. And therefore, convergence of integrals is not guaranteed. So, assuming the convergence in the first part of the conjecture, we obtain a Hecke operator, which map from smooth functions, smooth half densities on stable bundles to half densities on stable bundles, density on stable bundles, twisted with value in line bundle. Now, the second part of the conjecture is that operators TV, which you consider as extend to commuting complex self-adjoint operators of Hilbert space on densities, and intersection of kernel corresponding kernel is zero. Assuming the validity, this is compactness conjecture. Assuming validity of compactness, we denote by H the Hecke algebra generated as a subalgebra and endomorphism our Hilbert space generated by these Hecke operators. We can consider the feminism of Hecke operator of a complex line bundle or on F points of curve with value and endomorphism. So if we have a section of this line bundle of minus square root of canonical bundle, we can define the corresponding eigenspace is a subspace in our Hilbert space of vectors, which so eigen vectors under our Hecke map. We define spectrum as a set of sections for which the corresponding eigenspace is not zero. And then we define for non-archimedian field, we define the Schwarz subspace as a span of these subspaces. The compactness conjecture implies the initial Schwarz space for archimedian fields. In the next 7 slides, I consider the case when our field is a complex number. And in the case when I can present a formulation of conjectural description of the spectrum in terms of SL2 orders. There exists an analogous description in the case of real fields, but I don't have time to discuss. So for the next 7 slides, our curve is complex curve. Our basic player in this case is an opera. So SL2 opera on a complex curve is a triple. When G is algebraic SL2 bundle, nabla is algebraic connection, and beta is embedding of square root of canonical bundle, such which the connection defines the morphism of this bundle with the quotient twisted by canonical bundle. It means a generic embedding in every point. Opera C is variety of SL2 operas. If you have any SL2 opera, G when defined by G hat, the corresponding C infinity bundle, and nabla hat, the flat connection on this bundle. Having C infinity bundle, flat SL2 bundle, and the connection, we can define the corresponding representation of fundamental group. We say the opera is real if this representation can be chosen such that image of fundamental group is contained in SL2R. Now the question is, what is the relation with opera? Why do we appear? And this is reason for appearance of opera is due to the following result of balance of Madrid. Let D be the algebra of regular differential operators on the square bundle of canonical bundle on our but and let's spec D with a set of homomorphism of this algebra to see. It means a spectrum in the usual sense as an algebra. And then Benson will prove that the algebra of differential operators commutative, its spectrum is the variety of operas. Now we consider algebra A, which is tensor D as the head. Of course, the spectrum is just square of the spectrum. And C, we have natural involution, antilinear involution. Algebra A acts naturally in a space of smooth sections of compactly supported half-density band. We define the Schwarz space. We consider as half-check a space of distribution on half-density, linear functionals. Any endomorphism of half-density defines endomorphism of the corresponding space of distributions. And in particular, we obtain a map from our Hilbert space to define a map from Hilbert space to distribution. We say we define Schwarz space as space of vectors of Hilbert space, such that the image under any action of any element in A in our algebra A still in the Hilbert space. For any element in the spectrum of A, we define the corresponding eigenspace of vectors in our Hilbert space. And we define the spectrum H, a set of points of spectrum. The corresponding eigenspace is non-trivial, non-zero. There is a result, which that if it's non-zero, it's one-dimensional. Now we can formulate the Schwarz space conjecture that we have our operators HX defined on the dense subset. We claim the closure of this operator is self-adjoint. The Schwarz space is stable on the Hecke operators. And the actions of algebra A and Hecke operators commute. They both act on Schwarz space and they commute. It's a color for any point in the spectrum of H and D, there exists the corresponding eigenspace is one-dimensional. It's preserved under action of the Hecke algebra, and therefore defines an element in the spectrum of Hecke algebra on our Hilbert space. Now we can formulate conjecture of the description of the spectrum. We have a natural embedding of the spectrum of Hecke of D on this Hilbert space H into the spectrum, an abstract spectrum. The first part of the Schwarz space conjecture implies that the map to the first component is an embedding. It's easy to show. Let oper H on the set of image of a spectrum under image of the spectrum of the on H under projection the first component. So we obtain some subset of operas. And we define oper H in this subspace. It's easy to show that this subset is contained in the space of real operas. Now the conjecture is that actually spectrum of algebra H, spectrum H it contains of real operas, and the map from the spectrum of the differential operators into the spectrum Hecke algebras on our Hilbert space in bijection. So this conjecture implies that the spectrum of Hecke algebra parameterized by real SL2 operas. So this is kind of Langlands conjecture in this case. There's also a conjecture about eigenvalues, so that the last slide about complex case. So let's fix an open. As follows from the previous conjecture, there exists a section, it defines an eigenvalue, which is section of a complex line bundle, which -1 power of canonical bundle. And here is conjectural formula for this section. Since O is a real operator, there exists isomorphism unique up to multiplication ±1, which means smooth flat SL2 bundle G in this complex conjugate. Since any SL2 bundle is SL2, we obtain the Hermitian pairing on the space of smooth section on G. On the other hand, part of the opera was embedding of a bundle omega 1/2 to G, which is the same as section of G twisted by omega -1/2. Therefore, Hermitian pairing on G defines a norm scatter product of a section with it conjugated, which is theta O, which is section of line bundle. Conjecture is that eigen spaces of Hecke operators is given by this section. Okay, this is the end of the second approach. There's a third approach. As I said, we construct, in this case, action of a Hecke algebra of some on subspace, but the space will be unfamiliar. And okay. In our second approach, we replace the stack band by its open dead subspace, subscheme of stable bundles. Such a replacement is inconsequential for a definition of Hilbert space, as usual, but it doesn't lead to natural definition of star space. The third approach is based on definition of representation on the space of half densities of smooth half density on the groupoid band. Conjecturally, this space is isomorphic to the Schwarz space. For a construction of the space of smooth half densities of band, we extend the definition of a smooth circle of line bundle from scheme to admissible stacks. So algebraic stack Y of finite up is admissible. If there exists a presentation of Y as a quotient of a smooth stack by the action of GLN where X is smooth variety. An admissible presentation of stack is realization as a quotient stack. An algebraic stack is admissible as union of an admissible substacks of finite time. If Y is admissible stacks, we let Y be admissible stack with the presentation and L in line bundle of Y. Now we define a notion of smooth sections of a line bundle admissible stack. We pull back our line bundle of kappa power of the corresponding line bundle. We pull back our bundle from Y to X. We obtain a line bundle on X and it's a smooth stack. So we have a notion of smooth section with compact support on X with various line bundle. The group GNNF acts on this space, and we define our space of section on Y of line bundle L to the kappa as a covariance under the action of GNNF. Where in case of Archimedean fields, we take covariance in the category of topological space with Fréchet topology. One can show the space does not depend on the choice of admissible presentation. So it's really well defined for admissible stuff. And the construction is covariant under open embedding. Like usually notion of function with compact support is covariant under open embedding. Now let Y be a stack with admissible presentation. And suppose it contains a dead substack with a smooth scheme. We denote by Y the preimage, which is open subset of X. Since Y stable is a scheme, the group GNF acts freely on Y, and Y stable is a quotient of U mod GNF. So as before, we take some kappa. We'll see, consider the space of compactly supported smooth section complex line bundle on F points of X. For any S, the restriction to U is a section of a corresponding bundle on U. Since the group GNN acts freely on U, the fibers of a projection from U to Y stable are GNN torsors, and the restriction of a section S to this fiber is a density with value in a line. So we can try to define the push forward to be the integral along the fibers. But the conversion is not guaranteed, since the intersection of the support of F with fibers of the map is not necessarily compact. Now it's an important example, simple example. Let's consider the case when Y is a cube of P1 and H is PGL2 acting diagonally on Y. So it's a quotient of a smooth variety cube alone by action of the group. And we take Y stable, a quotient of U by H, where U the open subset of the sting point. Since H is simply transitive on U, U stable is a point. Then du by H invariant measure, H at F invariant measure on U. We fix compatible all structures on H and P1. It is now made du the product of HO invariance measures on P1 of F, which is H invariant, which is H of O invariant measure on X. A choice of all structure provides identification of a space as couple space of smooth functions on our cube of P1. Under this identification, push forward, which is function of a point, it's a number, is given by the integral, where this strange matrix is the ratio of the two measures on Y. One that was HF invariant, and one came from measure on P1. This is absolute conversion for all. So you see that not for all kappa push forward is well defined. Now we give a definition. A pair Y and Y stable, as before, we say kappa nice if push forward is absolute conversion for any S and defines a continuous section of a corresponding line bundle. A pair is excellent if kappa nice for all kappa bigger than 1/2, and in addition push forward, which is half density on Y line, is square integrable for any S. If pair is kappa nice, we can show that this push forward really finds a morphism for sections Y to the kappa densities on Y stable. And if pair is excellent, we obtain a map from half densities on Y to Hilbert space of half density on Y stable. Now we come to Hecke operators. We can see now the case of when our stack is bound. So when our band, we have its union of open substacks. The claim is bands are open admissible substacks of finite type. Let's see the Hecke correspondence. Since morphism from Z to band are smooth and proper now, because they don't restrict to the stable part, we have well-defined Hecke map from which is a dimorphism of S, which is S is half sections, half densities on band, and twisted in section of minus minus square root of canonical band and the corresponding Hecke operators. As before, we write H as a Hilbert space of half densities of band and denote by H as Schwarz space. The conjecture is that this pair is excellent. In this case, we have a map, as before, from half density on band to this Hilbert space. And conjecture is symbolic, and image is a Schwarz space. So this conjecture relates the construction of Hecke algebra outlined in the last two sections. In the last couple of slides, I explained the connection with the first approach. Assume now, and in the case of the first approach, that f is non-archimedian, and the curve is defined as move of C. Since the stack band is defined over O, and line bands are trivialized, either line bands are trivialized. Therefore, projection from O to ON, reduction as power maximum deal, define a linear operator from a pushback from functions on band over ON to function to densities OO, where space is then defined in the beginning of the talk. Conjecture that our space of half densities on band is union of images of spaces defined in the beginning of the talk. The restriction of subspaces to cuspidal space is a unitary embedding. And the image, the whole image is cuspidal image of cuspidal space subset of a set. It has a finite codimension in the image of all functional set. So this conjecture implies the existence of unitary embedding of cuspidal spaces defined in the first part of the talk to Schwarz space compatible with actual Hecke operators. The map from all sections to Schwarz space is not embedding because definition of Schwarz space or space half density involves the passage to coinvariance, which could have non-trivial kernel. This is the end of the talk. We're glad to answer questions if there are any.
Okay, so thank you very much, David. I have a question while there may be more questions on Discord. So your talk is mainly discussing the case when the group is PGL2. So can you say what you expect for a general reductive group?
So for a general, yes. Do you hear me?
Yeah.
Yeah. So in general reductive group, I expect to have a similar picture, but all definitions become more cumbersome. And one should be more careful with definition of Hecke operators. But essentially, I expect to see the similar picture in the case of arbitrary split, semi-simple or reductive group. But precise formulation requires more homework.
Okay. So I don't see further questions in the chat. I thank you very much for your talk. That's it.
Okay. Thank you. Bye.
Bye.